Thank you for being here. I was not expecting so many people also here. And today I'm going to present some works that has been particularly important in my research, especially from the point of view of supervision of work of PhD researchers. I try to select, to cherry picking also works that, let's say, tells a story in a certain sense about a topic, which is whole body contact-rich motion planning and control of floating-based systems. So I will somehow repeat a little bit a short bio for, let's say, the non-French listener. So I got a bachelor in electronics engineering and a master in robotics and AI at the University of Rome La Sapienza. And then I got a PhD in life and humanoid technologies at the University of Genoa and Istituto Italiano di Tecnologia. So during this period, I also had the opportunity on participating to the DARPA Robotics Challenge in the Workman team. I mean, in that period, my main topic was about whole body control for humanoid systems. And I was also visiting doctoral student at the Tokyo University in the Nakamura Sensei Lab. Then I had a period in IIT as postdoc and then researcher, first in advanced robotics department and then in the humanoid and human-centered mechatronics lab, working again on optimal control and model-based planning and control of floating-based systems. And then I got tenured in Inria with an ESFP, as ESFP, first in the Larsen team, and then now in the HUCEBOT team led by Serena Ivaldi. I also had, let's say, some experience in industry, always in research and development. First in Palo Robotics as robotics engineer doing SLAM, so completely different things. This before starting my PhD actually, then as a senior researcher after the period in IIT, working again on optimal control mostly, and closed chains, let's say, for humanoid systems. And then an experience in Leonardo SPA, which is a defense and aerospace company where I was a principal investigator of a team named Robotics and Autonomous Systems. Okay, so most of my, let's say, activities in research has been always under national and international projects. In particular, you can see, I mean, many European projects, and the one in bold are the one that, let's say, in which the work that I'm going to present were developed. Then experience in Italian national project, French national projects, Merlan in particular, which is my GCGC, which I will present you later. And then some experience also on a project for the European Space Agency between IIT and Leonardo for the Mirror project. Okay, some service for the robotics community, in particular, I mean, I was and I am associate editor for major RAS journal and conferences, co-chair for the technical committee for whole body control, associate vice president for the member activity board. I've been member and in the organizing, let's say, some conferences and workshop and special issues on my topics. And summer schools, and I am senior member of IEEE since 2024. I have also some activity from the Université de Lorraine, which is part of my actual contract, in particular mentorship for parkour research and internships. I'm helping Professor Bernardetta Addis with the exercises of operation research. And this year we organize also the course for Foundation of Robotics supported by Dr. Fabio Amadi. There are, of course, the co-supervision activities, which are, I mean, the core of these presentations. In particular, I'm going to present the work of 3 PhD students when I was in IIT, Arturo Laurenzi, Francesco Ruscelli, and this is the best picture that I have of Francesco, and Luca Rossini. All of them graduated at the University of Genoa. I am actually supervising 3 PhDs from the University of Lorraine, Ioannis Tsikelis, Ioannis Lezou, and Georgios Kalakonis. And then in the past, let's say, also several masters and a parcours research from the École des Mines. Okay, some context and contribution. My whole research since my PhD has been around leg system, in particular humanoids, but in general leg system and so floating-based systems. And I think that these systems has several advantages with respect to classical mobile-based manipulators, because they can navigate fully 3D the environment, they can exert high level of interaction forces, and they can really manipulate also both object environments in a very advanced way, let's say. Of course, to achieve this, they must autonomously select where and when, let's say, attach contacts and also establish contacts, and also respecting balance and also, let's say, control the contact forces accurately. And this kind of issue, this kind of problems leads to what is called the multi-contact planning and control problem, which couples together planning and control under contact constraints. So the multi-contact planning and control problem has several challenges. In particular, we have a very high search space because we are considering robots that are complex. So we have the robot we normally plan on the robot generalized coordinates and their derivatives, contact forces, and contact sequences. This problem is highly nonlinear and non-convex due to the robot kinematics and dynamics, the environment. Non-convexity is given also by, let's say, stability, and so on and so forth. And then the problem is also mixed integer, because we have to plan contact sequences and phases. So in general, I would say that solving the multi-contact planning and control problem corresponds to solve a non-convex mixed integer nonlinear problem. So I'm going to present some contributions on 3 topics that together can tackle, let's say, the multi-contact planning and control problem. So first of all, whole body control, which has been, let's say, my major topic since my PhD, which in his original, let's say, way, it's an instantaneous or reactive controller that permits to map operational space commands into joint space, taking into account the whole body, of course, of the robot, so all the degrees of freedom, priorities between tasks, constraints, and so on and so forth. Now, instantaneous controllers are not enough, so we need something that can plan taking into account also an horizon. For this, there is optimal control, which is a technique that permits to compute a sequence of actions and states in order for a dynamical system in order to minimize a cost subject to possibly constraints. And then sample-based motion planning, which is a technique that computes a sequence of states to bring the system from a start to a goal, sampling in state space, but I mean, not only, while accounting for constraints. Okay, so the first contribution is about a QP-based hierarchical whole-body Cartesian impedance controller, and this is a work that is a personal work, is not a work from a PhD student, but I was helped by Arturo Laurenzi that was starting his PhD. So the work is called the Multi-Priority Cartesian Impedance Control based on quadratic programming optimization, and the idea was to frame using an inequality hierarchical QP controller, QP framework, the Cartesian impedance control. Because while QP controllers at that time were, let's say, used for inverse dynamics and inverse kinematics, Cartesian impedance control was not really framed into that type of framework. And the idea was, let's say, to use, let's say, a parallelism that can be done also that, I mean, in classic inverse kinematics, in which we know that the pseudo-inverse solve an equivalent QP in which we minimize joint velocities subject to the task that we want to perform, and can be shown that this is also for J transpose F, okay? We are minimizing the torque subject to the task that we want to perform. And this can be shown also for priorities using the dynamically consistent pseudo-inverse. So the idea was to let's say, use this parallelism and frame it under a sequence of QPs, like, I mean, the classic inequality hierarchical QP framework, in which the tasks which are more important are solved at the high level in the first QP, plus some constraints in this case, and then the solution of these, so the optimalities of this task become priorities for consequent, let's say, QPs. We tested this on what will be the, so you see here a young Mingo, what will be the upper body of two robots from the lab of Nikos, which are the Centauro and Command Plus robots. And you can see here that I am, let's say, pushing the robot while the arm is doing another task. Here I set some level of, let's say, null space stiffness, Cartesian stiffness for the arms, and so on and so forth, and taking into account also torque limits. Okay, so the point of this work was then to introduce the first work that I actually supervised with a PhD. That was a work from Arturo Laurenzi called the Balancing Control through Post-Optimization of Contact Forces, which was basically the extension of this framework to floating-based systems. In particular, we wanted to tackle a particular set of works which uses two stages optimization, in which first a pre-optimization is done of the contact forces, taking into account the single rigid body, and then those forces are mapped to torques. This is different with respect to classical formulation, in which you have a single QP optimized for joint acceleration and contact forces. The problem of this two-stage optimization was at least the fact that you had to specify somehow the angular momentum, which is not really directly connected to the orientation of a part of the robot. So the idea here was to reframe so to consider basically a fully actuated system and rewriting the dynamics to have something which is basically what we were solving in the previous work. So we could use exactly the previous framework for Cartesian impedance control, and then mapping the branch that we obtain at the base into contact forces, and then computing the torques that we want to send to the robot. So this, again, to keep a two-stage optimization. So we tested this on simulation, both on the Centauro and the Command Plus robots. You can see that the robot, when picking the box, hits with the knee the table, but the controller is, I mean, capable to handle this kind of disturbance. And then we tried also on the real Command Plus robot. You can see that on the left I was having the hair and the robot was not having the head, while on the right I was not having more the hair, but the robot gained a head. And this was the best that, I mean, at that time we could do in terms of having a full body pure torque controller on the real robot. I want to, I mean, notice also for some, I mean, at least for someone, that this robot already was presenting closed kinematic chains for the ankles. Okay, so this set of work presented a framework that was able, a formalization of the Cartesian impedance control also for floating-based systems in a QP-based, inequality hierarchical QP-based controller. The main drawback was basically the fact that the first optimization stage could create a branch in the base that cannot be done with the actual contact forces. And this to reply to Olivier also, despite this can be used to trigger an action, the fact that you cannot really achieve that, we didn't explore much on that direction. But also, while writing the HDR, of course, this framework could be reframed as a single optimization, okay? Perfect. So the second set of works is about locomotion for quadrupedal and bipedal system using template-based models and optimal control. And the first work is another work that I supervised from Arturo Laurenzi, and is called Quadrupedal Walking Motion and Footstep Placement Through Linear Model Predictive Control. And the idea of this work was to extend a work that was quite famous in bipedal locomotion about that was a line of works like walking without thinking about it, in which you have a QP that so a linear MPC that can also plan not only using the linear inverted pendulum, not only the trajectory of the COM and the ZMP, but also the footstep where the robot should place the footsteps in order to maintain balance. And the problem is that this work was not extended at that time to quadrupedal system, at our knowledge at least. And the problem was the fact that the constraint to achieve this is this one, which is nonlinear and non-convex for more than two, let's say, footsteps at the same time. And so how they did it in bipedal system was to say, okay, we consider single stances, left and right. These constraints become linear, and so I can solve it in, let's say, classic QP. Of course, I cannot have a single stance, or at least in a normal locomotion for a quadrupedal system, I cannot have a single stance. So what was the trick here? Instead to consider a single linear inverted pendulum, we consider two parallel linear inverted subsystems, sub-linear inverted pendulums, dividing the robot in a front and back, but this could have been done also for lateral. And we were then optimizing using exactly the same technique, each of these, in the same QP, of course, in the same problem, each of these linear inverted pendulum. And then we could reconstruct the original system through a linear combination of the two subsystems, and in this way ensuring that the ZMP was remaining inside the support polygon. And this was done through a distribution factor alpha, which was not optimized between 0 and 1. And this distribution factor was basically deciding which part of the two subsystems was sustaining more the weight of the robot. So these are some results from using Centauro. And of course, then everything is mapped through the robot joints using whole body inverse kinematics. So this robot has more than 40 degrees of freedom. So using a template model was indeed valuable, okay? And here, basically, Arturo is sending velocity references to the center of mass only, while the algorithm is deciding where, the MPC is deciding where to put the contacts. So this is instead applied to the normal bipedal system. Okay, the second work on this direction is from Luca Rossini, and is called the real-time approach for humanoid robot walking, including dynamic obstacle avoidance. And for this work, the idea was to, first of all, move to nonlinear MPC, using still template models, so in this case, single rigid body, so to check how this performs, and also including the possibility to have some obstacle avoidance. This work was done by Luca during this period, so in collaboration with the University of Texas at Austin, in the lab of Professor Luis Sentis. And we came out with this framework in which we have an offline planner, which gives us footsteps to navigate a known environment. Then we have a contact space local planner, which is going to change locally somehow this plan. And then these footsteps are passed to the single rigid body MPC, which tracks the footstep in the sense of a cost. And this permits to being more robust to external pushes, okay? So we allow the robot to move a little bit around the planned contacts. And then everything is mapped to whole body inverse dynamics to the robot that here you can see was a simulation of the Draco 3 developed by the lab of Professor Sentis. So the idea of the contact local planner was basically to use some concept from SLAM actually, because what we did was to take the plan that was computed by, I don't know, RRT for example, and then we did another graph in which we have each footsteps representing a vertex plus the objects, let's say, in the environment. And then the edges are constraints or error functions, which are, for example, the relative distances between the foot or consecutive footsteps and the distance with the object that we don't want to collide. So every time, let's say, the object moves, that we know that the object is moving, the graph is re-optimized locally in order to keep a balanced graph. And this is similar to what is done in SLAM. And this, I mean, I think this was a very nice idea because this could permit to change dynamically also much more complex plan that could be given by, again, classic RRT or whatever. So here in the video you will see first the robot running on, let's say, straight footsteps and while being robust on external pushes, which were quite strong. This we could test only in simulation because the robot was not ready. And then here the change of the, let's say, plan online while entering inside, while moving the obstacle. And here we are moving the obstacle, but we can suppose that a camera could give us these information. Okay, so for this work, let's say, I would say we did several studies on, let's say, template-based locomotion strategies. The main drawback, in my opinion, of these works are, first of all, the fact that the obstacle in the second work are considered only at the foot level, and in general, the use of template models limits the dynamic capabilities, okay, during locomotion. For this reason, we started, I mean, from my work, well, since I'm here, we started to develop some whole body model predictive controllers. In particular, on the left, this was a collaboration again with Arturo, Luca, and Francesco. We ran a whole body LQR controller online on Talos. This is open loop, very surprising. Also because to make it work, we just had to run a joint impedance current controller, I would call it, the most basic way to do a joint impedance controller without even compensating for friction, nothing. And this was enough to give the compliance that you need, that you require during contacts of the locomotion. While on the right, this is a collaboration with University of Patras. We did a whole body MPC using sequential quadratic program. Here we are using HPIPM for the inner QP, and we achieved, I mean, everything is formulated considering the SC3 manifold, and we achieved around 7 millisecond MPC for 20 nodes. And here you have all the dynamics and kinematics and constraints. So, I mean, these are, I think, very nice results. So the final work that I'm going to present is a contact-rich motion planning and control framework. This is a work that I mean, is very important for me for multiple reasons. First of all, this work was in collaboration with my former university and lab and professor Giuseppe Oriolo and his PhD researcher Paolo Ferrari in La Sapienza. This work from we had also contribution from Luca, Francesco, and Arturo, and it started during the COVID period. So we really had to organize carefully meetings, the repositories, and so on and so forth, and we achieved indeed at the end to do also real experiments. So the work is called the Multi-Contact Planning and Control for Humanoid Robots, Design and Validation of a Complete Framework. And the idea was to really attack the multi-contact planning and control problem, and also using it, deploying it on a real system. So we used we used sample-based planning and stance before motion strategies. In particular, we developed this framework in which we have a planning layer and a control layer. And the planning layer accepts, let's say, a description of the environment that can be sampled. I will present mostly the planning layer, which is divided in stance planning and whole body planning. Now, the stance planner is basically permits to navigate manifolds, which are the stance manifold for the system, and in particular, we want to find configuration in the sub-manifold of the stance manifold. So, a configuration of the robot to be part of the manifold of the stance has to satisfy the forward kinematics. So we have some contacts that have been sampled, and we want to have the forward kinematics, let's say, satisfied. And in particular, to be part of the submanifold, we have some conditions, which are joint limits, collision and self-collision avoidance, and static balance. And the static balance solve, again, a QP, very similar, which is very similar to the one that we were solving in the first series of work. So what we did was to construct a tree in a RRT-like style, in which each vertex has a stance, and basically we expand the vertex, adding or removing a contact. Each stance gives us which frame is in contact, the position of the contacts, and the type of contact that can be point of surface. The configuration that satisfies this is generated with another work from Luca, which is called null space posture generator, which basically tries to use the null space of the system to generate a configuration of the robot that satisfies some constraints. And you can see here some examples on tiles. And then, of course, also the branch that realizes the static stability. So, for example, here you see for moving from 2 consecutive 4 constrained end effector stances, we need to pass through a 3 constrained end effector stances. Of course, we need also to generate motion plan, a motion path within each submanifold. And to do this, we used a work from Francesco, which is called a multi-contact motion planning and control strategy for physical interaction task using a humanoid robot, which basically was a work using OMPL and in particular Atlas RRT star, which builds, let's say, an approximation of the manifold, and so you can directly sample for in this manifold. And once you have all these states that are connected, that together, that brings you from one pose to another, then we connected them interpolating using trajectory optimization on cubic splines, and then a further contact manifold projection. And this strategy was also used for the work that we did for the ESA robot, for the co-design of the ESA robot. So these are some results of this framework. You see the creation online of the stances and the configurations, and then the final trajectory that permits us to move from passing through the various computed configurations. I will show you maybe, am I going too fast or too slow? It's fine. So maybe, okay, so the robot basically has to use, you see that it starts in double stance, goes to 4 stance, 3, and then back to 2, using the wall to rise. And of course, being quasi-static, this robot was not really built and designed for this kind of motions, but now these one are some other scenarios in which you can see also the contact forces, and we tackle also the chimney case or stairs, and here you can see the same scenario but with the contact forces, okay? and we also we were able, and this was really a big effort from Luca, to run the experiment on the real system. Here is briefly the control layer, which is formed by a reactive balancing controller, which is computing the torques given the planned force and also taking into account the actual configuration of the robot. The stance switching, which moves the let's say the limbs that are not in contact, taking into account constraints and so on and so forth, using whole body inverse kinematics and a joint impedance controller. And then the contact branch estimation, which actually helps to understand, because I mean, replanning, you know, the plan directly could not work, of course, and because maybe you are not in contact at the same time and so on and so forth, and so this helps us to understand when to move and when to switch contacts and so on and so forth. And in this particular phase of the execution, you can see that the robot needs really to push hard on the environment, and you really can see that the importance of controlling the force inside the friction cones and so on and so forth. Okay. And the robot achieved at the end. But you can see here there is a 6. So the motion are super slow. Super slow. And this, I mean, also to answer to one, let's say, comment from Professor Chevallereau, I agree that the main problem of this pipeline was that it was based on quasi-static regime, okay? Despite the fact that I think that extending the planning to more dynamic actions could be done, because you could allow, for example, the planner to remove more than one contact, allowing for jumps, no? But then you cannot, I mean, you need something that is smart and plan the trajectory, no? For example, trajectory optimization again, but more considering, for example, more nodes and so on and so forth. On this direction, we started some works, again, collaborating with other friends, I would say. The one on the left is a work from Ioannis Tsikelis at the first year of his PhD, and we wanted, in fact, to achieve more dynamics motions. We considered, again, the chimney, and we achieved these ninja-style, let's say, motions. Here we are using B-level optimization, which is a technique that I really like, because it can be used to solve, indeed, mixed integer nonlinear problems. And so here the outer loop is selecting the integer variables, the inner loop is solving the nonlinear problem. So it's slightly different than the previous approach. While on the right, we are using this same B-level optimization. This is a work with University of Trento and Professor Focchi to plan the motion of a robot that is suspended with two ropes, and there is also a sort of leg that can push on the wall. And so we need to select where to jump and compute trajectories. And so what we do is to select the convex areas of the map, and then to do the B-level optimization on these convex maps, patches. And this remembers me a work from Tedrick, which is called Planning on Graph of Convex Sets, which I don't know if you know, which is very nice. And I think that, I mean, some aspects are very similar, in my opinion. Okay. So, this is the final part of the presentation, in which I give you some idea of what we are doing right now, a part of the work that you already saw, and some perspectives. So, my actual work is mostly on my GC Merlan, which stands for Multi-Link Robot Empowered by Whole Body Local Manipulation. And the idea is to try some frameworks for planning and control of strenuous tasks in structured and dynamic environments. And for me, a strenuous task is a task in which you have high level of interaction forces and multiple contacts that can happen, between the robot and the environment, of the robot and objects. The idea is also to try to bring together, so all the work that I presented were model-based, pure, but the things has changed, as we know, okay? So the idea here is to try to find some smart ways or effective ways to put together model-based and reinforcement learning or imitation learning. So we tested these kind of approaches in the lab. There is the work of Fabio that is doing on this direction. And I mean, RL works great in this kind of system for this kind of tasks. So I perceive it as RL stabilizing whole body motion references. Then you have domain randomization, which helps you for robustness and simplifies sim to real. I mean, you don't have issues of real-time safety, or no, inference is normally quite fast. And so we are also, I mean, in parallel, so what I'm trying to do in my research is to keep 2 tracks, which are the classic my work on model-based, which is, I mean, which I love, and I think there are many things, and then trying, when I decided to come here in the lab of, first in the Larsen and then now in HUCEBOT, was also to understand better reinforcement learning and learning methods. So keeping these 2 tracks in parallel, but find also a nice way to blend them somehow. So here are some works on reinforcement and imitation learning. On the bottom left, this is a work from a student from the École des Mines, in which we are trying to do voxel to joint, let's say. So navigating the environment using the LiDAR, building them up. So in here we are trying to use both some classic approach for SLAM plus some memory inside the policies, and so some ideas, let's say, in this direction to explore the environment. Then there is the work of Fabio, top left, in which we wanted to show that it was possible even in a complex robot like Kangaroo. So this is a robot from PAL Robotics, in which presents multiple closed and parallel chains to directly do learning on the motor side. So, and for locomotion in particular. So here you can see the various mechanisms. So if you can basically model them in the simulator, then you can do also learning on that, basically, using that. And then this on the right, this has a motion tracking policy toward, let's say, loco manipulation tasks. However, there are still some problems also related. Of course, I mean, this method doesn't solve everything. There are some problems, for example, reward shaping, if you use only RL, for example, particularly if you use only RL. Data and computation hunger, so you need a lot of data, you need to generate this data, you need people that want to wear the suit to do the motions, and so on and so forth. It's costly, time consuming. You have poor explicability and constraint satisfaction, or at least you cannot certify them. There is a problem related to what and how much to randomize. So we wrote also a project on this, because domain randomization is nice, we can apply it, but knowing what to randomize and how much to randomize is still an issue. And I mean, mostly these things are done to experience, okay? And then there is this thing that I wrote, wakey joint references, which means that most of these policies outputs joint positions that are tracked by a joint impedance controller. But if you check the tracking is not good. Still, the policy works. So this means that the joint position is a proxy for the torque control. And this is very strange with respect to what we use in classic, let's say, control. I think that these aspects can be tackled by model-based planning and control, for example, using trajectory optimization to generate the data, and so on and so forth. The point is to find a nice way how we should put them together. So this is another work, and I mean, here I give two examples, and then I'm going to close. So this is a work from, again, from Ioannis, in which we want to do a massive parallel nonlinear problem trajectory optimization. And the idea is that if we can solve a nonlinear program on the GPU in parallel, then we could, first of all, run the B-level optimization massively in parallel. And here you can see in the video, so here we are solving at the same time 16,000, more or less, 32,000, yeah, 32,000 problems, nonlinear problem for, I mean, this is a very simple system. It's an inverted pendulum. Here I'm showing only 64, but in fact we were solving 32,000. And keeping more or less same solution time. Another point is also that if some parts of this problem are networks, then we could imagine to use this solver as a layer in our policy, enforcing constraints, enforcing a little bit of, let's say, explicability, and so on and so forth. This is another work from Fabio instead, which is the other way around. So to train RL, inputting MPC references, but also teleoperating the policy using MPC. And here we can see that we can, I mean, move the arms and locomote at the same time on the real robot. And the idea is to try to exploit the future information that we have on the MPC. I mean, I took this title, MPCRL, because there was a paper that came out recently on this kind of, let's say, approach. So it's, I mean, a nice direction. But also to try to find a way to train directly the policy using the MPC. So I conclude with some mid and long-term research directions. So I have some research objectives, which are basically 3 research objectives about reasoning, planning, and executing. So I think that robots, especially I mean, humanoids that we are seeing, are becoming more and more famous. Once deployed on the wild, they will have to reason on the task that will be given them using, for example, natural language, okay? I don't think that we will, we want people to, even using simplified programming language, the task will be given by natural language. So the robot will need to understand using, I don't know, large language models, whatever, relating with the environment, relating with the object in the environment, and so on and so forth. It will have to plan in long and medium term, considering again the environment, its own hardware and the objects, and so on and so forth, and of course to execute these plans. And it's not only executing, but also monitoring, no? Because something could go wrong, or something could diverge from the initial plan. So on this direction, let's say, on these research objectives, I have some axes, let's call it, in which, in particular, I'm considering planning and control through numerical optimization methods, because I think that this, I mean, no matter is learning or model-based, I mean, an important block is the optimization. And in particular, I would like to follow on, find ways to resolve mixed integer nonlinear programs, especially for contacts. I mean, trying to do not go toward the direction of the complementarity, okay, if possible. Then, of course, the second axis is planning and control to models and data, which is basically what we are already trying to do in the Merlan, so to try to merge in a more effective way model-based, in particular in the robotics context, of course, and learning methods, and then planning and control and computational design, because I mean, there are a set of work that I did about computational design, which is basically not only computing a plan or an optimal plan or an optimal controller, but also computing an optimal hardware to do the task. Now the problem is that a bottleneck most of the time is that you compute an hardware for a specific task, but maybe we could extend this concept and having, let's say, hardware which is optimized on multiple tasks at the same time. Okay, so, or mechanisms, because this can be extended to any type of, and of course, I mean, going more toward parallel computation and this kind of switching of paradigm can help also these computational design aspects. Considering the application scenarios, instead, I mean, we wrote some projects recently on using humanoids or in general heterogeneous legged systems in construction scenarios. Unfortunately, it didn't pass, but okay. But still remain, in my opinion, a very nice application, very useful because, I mean, the robot is used to really help workers on strenuous tasks. And for this reason, Merlin was framed in this direction. And also because I think that once we will be able to deploy the robots in this kind of scenario, we will be able also to deploy robots into caregiving and house tasks. Not because I want to destroy kitchens with high interaction forces, but because I think that when you have an elderly person, you cannot only think to prepare the meal. You need also to think that this person could fall, so you need to rise or move the person on the bed, which means to really have to exert high level of interaction forces, but in a very careful way. And then the final, I mean, very maybe long, but I hope not so long term, to deploy legged or in general multi-limb system into more extreme scenarios like space or underwater, because in there we have a lot of challenges related to generation of motion and interaction. For example, conservation of momentum, for example, drag forces, and so on and so forth. Or motion in low gravity, okay, interaction in low gravity. There is also another aspect which is more far from my actual research, but we were discussing this a lot, especially when I was in Leonardo, that is related to the coordination of heterogeneous complex systems. So like multiple humanoid robots cooperating together, or humanoid and dog robots, or quadrupeds, whatever. And I think this is also a very interesting research direction, because then, of course, you have to generate motion according to the capabilities and the skills of these robots. And okay, I think it's enough. I thank you very much. This concludes the presentation. I want to thank the jury again, to thank Serena, of course, because she pushed me a lot since I arrived here, and she pushed me in the right way, and I achieved really a lot. I want to thank JB. Thank you, because he's the best reviewer too that you can have. And the lab, the people that, of course, participated to these works that I showed, and my wife, Silvia. Thank you.